Welcome back. This is an Aleks training video on calculating radioactive activity from half-life. So, you have got two ways that you calculate radioactivity. The first one is in becquerels. Okay, becquerel was one of the earliest guys to study radioactivity. And the second one is in curies, also a famous scientist who studied radioactivity. And I'll give you the equivalent in a minute. Well, let me write it down. There are 3.7 times 10 to the 10 becquerels in 1 curie. Okay, so we'll use that at the end. The other thing is that you're asked to find a rate, okay, how fast. So iodine 131 is radioactive and has a half-life, okay? So first of all, you know what its mass is. You know that it's 131 grams per mole. You know what its half-life is. It's 8.04 days. And you're trying to calculate the activity, how radioactive is a certain amount of milligrams of it, okay? So how radioactive is it? So the first thing that you're going to need to know is that your rate, how radioactive what is its rate, is first order kinetics. So that's going to be a rate constant times, not the molar concentration as you've done in kinetics, but the number of in this case, number of atoms that are radioactive. How many things are spitting out stuff? Okay, the rate of it is based upon the rate constant times the number of radioactive atoms you have. Okay, so let's find out how many radioactive atoms we have, and then we'll find out what our rate constant is. Let me tell you the rate constant. This is first order kinetics, and this was from chapter 15, the natural log of 2. It's your LN button on your calculator divided by your half-life. Okay, and your half-life has to be in seconds. Let's go ahead and do K. The natural log of 2 is a constant. It's always the same, 0.693. You just put 2 and then push the LN button on your calculator. It's 0.693. Your half-life has to be in seconds. Okay, so I'm getting my calculator right here. I'm putting 8.04 in the calculator, days. Now I want seconds. So I'm going to multiply by 24 hours in a day. Now I'm in hours. Times 60 minutes. Now I'm in minutes. Times 60 seconds. Now I'm in seconds. So this is going to be 694,656 seconds. So this is my K. So divide that out. 693. Okay. And I get my K equals 9.98 times 10 to the minus 7. Okay. Now I need my N. My N is 1.1 milligrams. Okay, to go through the periodic table, I have to get to grams because I have to go to moles. So there are 1,000 milligrams in a gram. Okay, and in iodine 131, you can't go to the periodic table. You have to go to 131. It tells you the mass here. So there are 131 grams per mole of iodine 131. But I don't want molar. I don't want the molar concentration. I want the number of actual atoms. So in 1 mole, I have Avogadro's number, 6.022. And I hate Aleks, but you have to look on Aleks. I would just say 6.022. Aleks goes ahead and puts 14 times 10 to the 23rd. Okay, so I'm going to 1.1 divide by 1,000 divided by 131 times 6.02214 times 10 to the 23rd and I have my N as 5.1 times 10 to the 18. These two multiply together. Okay, so times 9.98. All right, we want two significant digits. So I have 5.0 times 10 to the 12 becquerels. And then I need to use this. This is becquerels. 3.7 times 10 to the 10 divided by 3.7 times 10 to the 10. And I have 1.4 times 10 to the 2 curies. Right, so I have two answers. 5.0 times 10 to the 12 becquerels and 1.4 times 10 to the 2 curies. Okay, that gave me a headache. I hope it didn't give you one.